Good time of the day, everyone. We're continuing the series of online technology meetings given by EPIC, and today's event is devoted to metamaterials and metalenses. Here's me, Ivan from EPIC, and my colleague Jeremy will guide you through this incredible seminar today. And today we'll hear 7 very exciting presentations given by the industry leaders in this topic. First, we'll hear about tunable metasurfaces and its applications from Samsung Advanced Institute of Technology. Then we'll switch to optical manufacturing services for metalenses and meta-optics produced at Applied Materials. We'll hear about the single lens cameras by the NIL technology and the meta-optics transforming sensing and moving optics into a semiconductor foundry by Metalenz. We'll also have the presentations about the nano-imprint lithography given by EVGroup and about the design of metalenses and metasurfaces by PlanOpSim, as well as the fully automated commercial tool for metasurface optimization by Synopsys. And apart from all the speakers that I've just listed, we have a record amount of participants in this online seminar today. We have over 250 registrants for the event. And on this picture here, you can see the representatives of all the levels of the value chain that are not today in the room with us. So please feel free to let us know if you want to get in touch with any of this. We have end users and system integrators, as well as manufacturers of optics, the materials and lasers. And of course, many of them are already working with the metamaterials and metalenses, the topic of today's event. Apart from this, it's very important that this event was enabled by 3 sponsors, which are Corning Laser Technologies, NIL Technologies, and axetris. And maybe my colleague Jeremy can tell you a few words about this. Jeremy?
Yeah, thank you, Ivan. So yeah, we have today 3 sponsors for this event. So NIL Technology, which is an optical solution company designing, developing, and manufacturing optical elements and components using high precision nanoscale systems. So we'll know more about the company and what they are proposing in the Metalenses field later in this meeting, since we will have a presentation by Niklas Hansson from NILT. So we have axetris as well as a sponsor. So axetris is a Switzerland-based company which serves OEM customers with micro-technology-based infrared light sources, laser gas sensors, gas flow sensors, and micro-optical components used in industrial, telecom, environmental, medical, and automotive application. They are multidisciplinary and highly skilled engineering and manufacturing teams combine broad experience in design, manufacturing, and metrology, from MEMS components to advanced optical and electronic sensors modules. And last sponsor is Corning. So we have Jess Wang who will introduce the company with 1 slide presentation. So Jeff, you can share your 1 slide presentation, please.
Sure. Let me share my screen. So good afternoon. Everyone can see my screen. So good afternoon for everyone.
You go on the full screen mode, Jeff?
Yeah. So?
Yeah. If you go in full screen.
Full screen. Sorry. Yeah. Sorry.
Thanks.
So,
perfect.
Yeah. My name is Jeff Wang. I represent the Corning Laser Technology to make a brief introduce for the team. And the Corning Laser Technology, show name is a COT, it's a part of the Corning company. As you maybe know, the Corning company is a material company, is a service over the 160 years. And one of the biggest model is focused on the brittle material and such as the glass or ceramic. So the Corning Laser Technology to provide the process solution for support those business. For example, like the Eagle XGO Lotus for the display and the high index glass or lower CT glass for the semiconductor application. So COT headquarters is located in Germany, And we also have an in-house design and development team. And we also manufacture our machine from Germany also. So let me show you one example for our business. Is named the WPS wafer precision solution. You can check the right-hand side is the classic model COT 500X platform, which is combined laser cutting process or dicing process and Dynatech separation process. So based on those solutions, we can realize to cutting the wafer or dicing or separation the chip in the wafer scale. So based on this one, we have a 24 years experience for laser knowledge, and we provide a high quality, high throughput, and high reliability machine to the team. So if you're interested for us, please visit our website for detail. You will see a movie, very fancy. You will see our core technology in the movie. So you also can mail to us if you're interested for the further discussion. So thank you for the team to provide the opportunity to show us in this successful meeting today. Thank you.
Thank you, Jeff. Thank you. And now we can switch to the presentations of our speakers for today. And we have the privilege to welcome Junghyun Park, the principal researcher at the Samsung Advanced Institute of Technology in Korea. And Junghyun will tell us about the Samsung's efforts in the tunable metasurfaces and its applications. Junghyun, the floor is yours.
Hi, Ivan, and hi, everyone. Thank you for your arranging, and I'm glad to be here to be able to share our research here. To begin, I'm working in Samsung Advanced Institute of Technology, or SATE, which is located in South Korea. And there are around 1,200 researchers in SATE working for diverse areas like quantum dot or battery and AI, computer vision algorithm. And there are around like 70 researchers working in the Photonics lab. And I'm one of the leaders in that lab. So today I'm going to talk about the tunable metasurfaces and its application for specifically a LiDAR. Okay. Yeah. So LiDAR, which is light detection and ranging, is basically a sensor that can measure the distance between the sensor itself and the objects surrounding it. And it can be used for various applications like autonomous driving here. And also it can be used in mobiles to improve the AR and VR. And also it can be used for gesture sensing. In order to implement it, there could be various approaches like the non-scanning method or scanning method. But the concept of using the mechanical LiDAR is that it comes with a bulky size and high price. In terms of the mobile LiDAR, there are already products in the market. One is from the Samsung Galaxy Note 10 Plus, which is based on the flash indirect time of flight method. And the other method is the iPhone 12 Pro's approach, which is based on the spot array and the direct time of flight. So those like technical terminology of the flash or spot array or scanning is a way of how to achieve the information for the theta x and theta y that comprises the three-dimensional information. And the other axis here, the vertical axis, indicates the indirect time of flight or direct time of flight, which is about how to extract the distance information. And here, my technology of the tunable metasurface falls into this category of the scanning method. So a typical LiDAR is based on the flash or flood illumination, and it can come up with a very high resolution, but it suffers from the very short ranging distance. In order to increase the range distance, we can think of using the spot array, but it comes the concept, the use of the spot array is that it has a very low resolution, like 8 by 8 or 20 or by 20. However, it can steer the beam, we can illuminate the scene with a very high intensity pencil beam. So it can overcome those like range and resolution trade-off. But the issue is that we have a good scanners which can be used for the mobile or autonomous driving. This one shows that some tree of approaches for LiDAR, and there could be many different ways of the mechanical rotation. But in order to make it robust to shock and vibration, we need to come up with some solid state method or non-mechanical scanning. And this is where the active metasurface can play a role. I guess everyone here could be very familiar with the concept of metamaterials and metasurface, but I could briefly recap the concept. So basically, the metamaterial is an artificial material that can exhibit some beneficial properties that cannot be obtained in nature. And metasurface is the two-dimensional concept of metamaterials, where we can control the flow of light at the deep subwavelength scale. And if you have a more deep categories in the metasurface, there could be some one group of the passive metasurface where the Metalenz or DOE falls in, and the other part is the active metasurface. So here in active metasurface, we change the signal, not just the shape or orientation, and the optical response of the metasurface depends on the applied signal. So we can tune the amplitude or phase or polarization, both or either. And here we chose the indium tin oxide as the material platform to achieve the active property or post-fabrication property. The nice thing about using indium tin oxide is that by changing the carrier concentration here, we can tune the plasma frequency a lot. And this one shows the dielectric function as a function of the working frequency. And as you can see from here, by changing the gate carrier concentration by external gate, we can tune the dielectric constant in a very wide range. And we put this active material of the indium tin oxide sandwiched between the top and bottom metallic antenna here. And we connected the separate applied bias, V sub T and V sub B. And as you can see from here, by using the different various combinations of the voltage of the V sub T and V sub B, we can actually achieve the 360 degrees or full 2 pi range with the reflectivity and phase fully decoupled here. So here the reflectivity is almost constant, around the 4%, and we can obtain any desirable phase here. And by using this kind of phase grating, we can tune the direction of the reflected beam within plus minus 5 degrees or so. And by using this kind of the tuner metal surface, we added some other modules like pulse laser and avalanche photodiode here. And we used the beam scanning method to achieve the LiDAR image here. And as you can see from here, our proof of concept shows some 3-dimensional depth map within like 5 meters or so. And hereby, I need to put some disclaimer that the vertical scan range here was done by some mechanical tilting. However, our team is working hard and made significant advances in the real time, the full 3-dimensional image with the extended range. And yeah, this is my presentation, and I'll be happy to discuss or answer to any questions.
Thank you, Junghyun, for this opening presentation. I'm sure many people are very excited about this research as you combine the two hot topics, which is metasurfaces and the LiDARs. I think these are the two topics that we almost address the most often at EPIC. And yeah, so now we're in the question and answer session. So please push the raise hand button in case you have a question for our speaker. And yeah, I see there is a question already from James from Nanobox. Please go ahead.
What's the next step for you in your development?
Oh, yeah. So next step is to make the small form factor. As you can see from here, this image was achieved, like on the breadboard. So the illumination part was kind of bulky, and APD was also bulky. So our team is working hard to make it in a small factor that can fit into the mobile phone. So we learned that there are many restrictions, like the power consumption and the thickness and the applied voltage range in mobile phone. So yeah, we will work on it. Another thing is that we made this concept in the 1550 nanometer, the wavelengths of the 1550 nanometer. And due to the cost of the receiver, now we are considering the use of the 940 or 905 nanometer. Yeah.
Okay. I hope that answers your question, James. Second question from Olaf von Hofsten, please.
Yes, thank you. My question was about the scan angle you can achieve with this. Why did you choose the 6 degrees? And is there a fundamental limit to this angle, or can it be increased?
Oh, yeah, actually, good question. I was hoping to answer the question. Actually, the field of view or field of illumination is dependent on the pixel size of this unit cell. So basically, in our structure, it turned out the pixel size or pixel, a pitch, was around the 400 nanometer. So in theoretical method, this field of illumination can extend plus minus 90 degrees, actually. But in order to make some proof of concept demonstration, we combined multiple antenna into a single big giant cell with the pitch of the 5 micron. So that's why we came up with a small field of illumination. But in principle, we can extend it a lot. Yeah.
Okay. Interesting.
Thank you, Olaf. Next question from Gabor from Huawei.
Hi, thank you. I have the very similar question regarding the resolution. What is the theoretical limit of the scanning resolution? I believe you indicated 0.2 degrees in this particular case. Can you go better than that?
Yeah. Yeah. Oh, yeah. Very good question. So the resolution, in terms of resolution, we need to think of the 2 factors. One is the beam divergence. If your beam is too kind of wide or fat, we might lose some resolution. And the second one is the number of addressable points in the field of view. Actually, it is dependent on the number of the independently controllable pixels. So in this work, we came up with 50 independent channel. So the total number of addressable points is equal to the number of the channels. So it was 50. But if you can come up with some vertical internal access or via, we could make a more complicated electrode structures, not in just the planar fan out. Then we could increase the number of the individual addressable channels more than 500 or so. So we think we can go beyond several hundreds.
Thank you. Excellent.
All right, and maybe the last question from Shinsung Ansys.
Yeah, so my question is the electrical tuning at this specific wavelength range seems to be working quite well, right? However, yes, that electrical tuning, the tuning range seems to be a little bit smaller than in visible wavelength range. Is that correct? So in that case, what might be the best feasible route for tuning at that wavelength, thermal tuning or whatever means? Do you have any idea?
So could you repeat the question? So you're questioning about how we can achieve the beam steering, the visibilism?
It could be the LiDAR application, but for general, the visible tuning, Metalenz tuning for visible wavelength range. That's my question.
Yes. Yeah, so there are some other groups working in our team who are interested in achieving the beam steering in the visible region because it can be used for a wide-angle holographic image and those things. And maybe, as you can see from here, the indium tin oxide, the working range is kind of limited because we cannot go very extremely high carrier density above 10 to the 21st or so. So to make it working in the visible rhythm, I think maybe we could think of the liquid crystal and some other metal surface structures. If you look for some work from the Professor Arseny Kuznetsov from A-STAR, they came up with a very brilliant idea of using the liquid crystal surrounding as a surrounding material around the titanium dioxide disk. So by perturbing the Kircher condition, we can achieve like 360 phase in a discrete level. So I think maybe liquid crystal could be a good platform to play around in the visible zone.
Okay, thanks for all the questions. And Junghyun, I'll just follow up with my own question. So now that you're presenting in front of all these industry representatives, and as you can see, many of them are very curious about your research. Is there something you are missing? Is there something they can help you with? Maybe with fabricating the meta surfaces, or what are the bottlenecks of the industry that you can identify from your point of view?
Yeah, the next thing that I hope to get some help or support from the industry regarding the active metal surface is that there could be some trade-off between the operating speed and efficiency and what did I say, the directivity of the beam. So I hope to learn from the society about some material innovation, because I believe there could be some other material platform that could allow us to achieve the high efficiency and high speed and low power consumption. Or maybe one of the candidate could be some phase change materials like antimony cellulite or antimony sulfide or something like that. So I hope to learn any advances from the society.
All right, that's very clear. And so I'm glad you brought up the question of materials now, because the second presentation of the session is given by Gauthier Briere from Applied Materials. And Gauthier will tell us about the optical manufacturing services for metalenses and meta-optics by Applied Materials. Gauthier, whenever you're ready.
Yeah, can you hear me?
Yes.
It's okay, you can see my screen also.
Yes, you're good to go.
Okay. Can you hear me?
Yes, Gauthier.
Yes, we can hear you.
You're good to go.
Yeah, sorry, I don't know why my microphone did not work. Yeah, first, thanks to EPIC to organize this talk. Thanks to Vera, Lieven, and Jeremy for the invitation and the organization. So it's cool. We are now a member of EPIC association since recently, and so we are really happy to share what we are doing in this topic. So I'm Gauthier Briere. I'm product marketing manager. And today I will talk about optical manufacturing services for metalenses and meta-optics. So first, some numbers about Applied Materials, if you are not familiar with the company. Applied Materials exists since 55 years now. We did celebrate the 55 years last year, so 2022. In terms of revenue, we are more than 23 billion for the year 2021. We are spending more than 2.5 billion in R&D and research. We have a huge portfolio of patents, especially in semiconductor and display, and we have more than 27,000 employees in 19 different countries. So I just would like to underline that today the group where I am is totally different from the normal business units that you are meeting with Applied Materials most of the time. Today I'm here as someone working for the engineered optics group. which is a group under the CTO office of Applied Material. And so what we do as a CTO office and at Engineered Optics, we literally use the skill and the experience of those 55 years working in the semiconductor industry to not anymore manipulate the electron as we used to do before, but to manipulate the photon. And so the Engineered Optics group is really based on a different business model compared to what Applied Material is doing. And so here what we are doing is that we propose optical manufacturing services for people who want to develop optical devices, such as Metalenses or Meta-Optics. And we also develop the product of our customer who cannot do prototyping or proof of concept, etc., etc., as we have already done in the past with some waveguide company, for example. So this is our two focusing for now. For example, we have the waveguide combiner based on diffractive grading, such as maybe you already know the company Penninck, where we realized on fully 300 millimeter transparent substrates, those kind of waveguide. And we do also for now Metalenses in the near infrared, the same where we control the full process on 300 millimeter transparent substrate. So let's discuss a bit about Meta-Optics. So I wanted to say a couple of words about Meta-Optics and if it makes sense to use Meta-Optics or not, because since I finished my PhD on that topic, I've heard some people who do not really think that Meta-Optics is useful. Today, I think it's useful, and we have some proof about it. We have some company like Metalenz and STMicro who show that you can do a product which makes sense. Meta-Optics is considered as a disruptive technology since recently, and so you have a full specification that you can do with metaspaces that you cannot do with classical refractive optics. So I'm not here to show you like the meaning of doing Meta-Optics. I think it's a question of finding the good product and where we can use those Meta-Optics and Metalenses like in a good way. But yeah, we have some proof that now Metalenses is really attractive. So what we can do at Applied Materials, so when you use this kind of metaspaces, you need to be sure about the quality of your nanostructure and the nanoresonators that you use to make your device. So everything I will show you now, it's between 10 devices, optical Metalenses, to 10,000 of Metalenses per wafer. And on those kind of wafer, we have like a full control of the geometrical parameter. So here I'm showing you two different examples. So the first example is the sidewall angle. So you need to have like a perfect form factor for this kind of nanostructure. And so here I'm just showing you that on those wafer, we have a full control for different diameter for those pillar, and the sidewall angle is fully controlled. We can also propose different services like putting anti-reflective coating at the back, or we can also do encapsulation. The other control we have, it's on the critical diameter. On those sample where you have like thousands of optical devices, we have like a total control of the geometry, which means that we have a 3 sigma, which is less than 12 nanometer for a range of diameter, which goes from 120 nanometer to 240 nanometer. So yeah, that's kind of amazing because you need to have like a full control of it, and we have it now. So I think I was going fast, but anyway, so if you need to, if you have any question or if you have like any ideas, that's the idea why we decided to become member of EPIC. We want to collaborate with people. We want to be partner with people. So do not hesitate to come to talk to me or to my colleagues from the business team of the Engineered Optics group. We will be at SPIE Photonics West, and our GM will have a talk where we will present our last result and discuss the technology we propose with our manufacturing platform. Thanks.
Thank you, Gauthier. Great presentation. And we already have the first question for you from Junghyun from Synopsys.
I'm just wondering, what's the fabrication tolerance? I look at the picture, it's very impressive.
Yeah, well, so that's a tricky question because it depends on your device and what kind of application you are doing. But the only thing, you can still see my screen, yes. So it depends. You know, that's complicated to talk about tolerances when you have like different size of nanopillar and when you have different height for some device. So it depends on your design rule. So unfortunately, today I can only show you those kind of results, but that's how I would characterize the tolerance. You have a 3 sigma inferior, less to 12 nanometer. After, it depends on your design rules, which kind of structure you are developing, etc., etc.
Thanks.
Okay, and Junghyun, so here's your material collaborator.
Could you comment on the wafer size, like 300 millimeter? And the second question is about the material platform that is possible in your system. And also, could you briefly comment on the available aspect ratio?
Yeah. So the aspect ratio, I would say, like now we can go up to approximately 800 nanometers, if I'm not wrong, with the same kind of pillar range. After, it depends also on the design rule and how we integrate the process comparing to your device. For the wafer, now we have a full control on 300 millimeter transparent wafer. We can also do 200 millimeter. It depends. That's also something we can discuss. And on the material, I would say anything, you know, high refractive index material you can put on transparent wafer.
Oh, I see. Wow, very impressive. Thanks.
Arseny from Snapchat, please.
Thank you. Gauthier, you mentioned that meta surfaces can be fabricated with the standard semiconductor processes, but then if we go into the visible range, such devices will require transparent wafers, and a lot of semiconductor equipment will not like glass wafers.
Yeah.
Can you comment on this and whether you think there is a room?
Yeah, so that's a really nice question because, you know, we have this debate in the Metaspace and Metalenz community since, I mean, even 10 years before I started my PhD, where people are like, okay, we can do Metalenz in broadband visible. Now I think that everyone agrees that we can't. We do not have like the theoretical approach to do it, and we do not have like the material approach to do it. Now I know that the resolution of those critical diameters that you are using for those nanopillar or any kind of shapes that you are using to create those metalenses or meta-optics are going lower and lower and lower and lower. So now it's based on the limitation on your scanner and how you do the lithography. But we are in the near infrared now, but I feel definitely confident that soon enough we could be able to do meta-optics really basics in the visible. It will take time, but I'm sure we can do it.
Can I ask a more specific question? Can you put glass wafers into your optical lithography tools at Applied Materials?
Yes, totally. That's our strong knowledge actually with the General Optics group. It's because we add all the skill and background for the waveguide combiner, which is typically glass transparent wafer, and that's the same kind of process and approach. So that's exactly what we know to do the best.
Mm-hmm. Thank you, Gauthier.
Yeah, thank you, Gauthier. There was still a question from Fraunhofer IOA.
Yes, thank you for giving the nice impressions. My question would be about the design rules you mentioned. So typically, you showed here we can see in this slide we can see a variation in pillar width or pillar diameter. but typically you have quite strong variation in structure sizes across one element from the meta surfaces. Can you give a little bit comments on that? How restrictive are your design rules?
I'm sorry, I cannot share our design rule without you know,
Yeah, not in
NDA.
detail, but general.
Yeah, it's you know, that's like every you know, more or less in the near infrared. Like, I think that if you take any kind of article or if you do some bibliography, you will see that for nanopillars with circular shape, you need to be between 100 nanometers and maybe up to 240, depending on the pitch that you are using. So I think we are close to that. Like, if you need to have an idea. And after, I need to say that it depends also on the optimization of the process, because not every design for those metalenses or meta-optics components are similar. So every time it's like an iteration and optimization of the process.
Yeah, and rather you're looking like rectangular bars than such pillar structures, right?
Yes.
And they should have sharp edges or corners.
Yeah. Yeah. So that's on our roadmap, polarization control pillar. Yes.
Okay, thanks.
All right. If there's no more questions, Gauthier, we thank you again for the nice presentation, and see you soon at Photonics West.
Yes.
And the next speaker is Niklas Hansson. He's a head of application engineering at NIL Technologies, and he will tell us about the single lenses cameras that they develop at NIL. Niklas, whenever you're ready.
Thank you for the introduction. So my talk today is about Metalenz cameras, and in particular the single Metalenz camera. The video that you see here is captured with a camera based on a single Metalenz paired with a sensor. And this was captured at Photonics West in Nils' booth last year. So cameras based on meta-optics is interesting for a wide range of applications. I would like to highlight time-of-flight sensors, presence detection, eye tracking, driver monitoring, LiDAR, as Mr. Park talked about before. But it's not only the RX side that is interesting, the receiver side, but it's also the emitter optics, using meta-optics to make flood illuminators like diffusers or dot projectors, or why not scanning LiDARs. Meta-optics is also a promising technology to make waveguides. At NILT, we have two different product categories. We have the meta-optics, which we use in order to make illumination and receiver optics for time-of-flight, LiDAR, driver monitoring, and eye tracking systems. So the emitter optics is fundamentally dot projection systems and flood elimination systems. But we also make bare lenses, can be collimators or focusing lenses. Then we make receiver modules, and these modules can be comprised of either just one single Metalenz, or it can be two Metalenses paired together, or it can be hybrid systems where you pair refractive optics with different meta-optics. On the AR, augmented reality side, we provide masters for making waveguides, and we also provide prototypes. And on these masters, we put slanted gratings and blazed gratings and binary gratings in different orientations. NIL Technology has its headquarters in Copenhagen, Denmark, and we also have sites in US and in Asia. The company is vertically integrated, meaning that we have both design, mastering, prototyping, testing, and mass production within the same company. This enables us to have fast prototyping, and also it enables us to design already from the beginning to the manufacturing tolerances. So what is so interesting about meta-optics? I would like to mention a few properties. First, it is possible to reduce the number of elements in a refractive camera, in a camera on the RX side. It's also possible to have multifunctionality, meaning that you can use angle of incidence or polarization to manipulate the output. You can also make it more compact. You can, for example, eliminate the lens sag because the lens is flat. And in some cases, you can also reduce the back focal length. You reduce the integration complexity since the Metalenz has the same form factor as the sensor. And moreover, the temperature stability is much better with meta-optics compared to refractive. Nilte is working on custom-made solutions with meta-optics ranging from the pure bare lenses to advanced hybrid solutions. Already from the beginning, Nilte was working a lot on trying to increase and maximize the efficiency of meta-optics. And we managed to reach a 98% relative focusing efficiency and 94% absolute focusing efficiency. You can see down to the left here, this is the simulated point spread function and also the measured point spread function, which is almost coinciding. So where does the light go that does not go into the imaging order, which is the first order? Well, it goes into the 0th order, which is light not interacting at all with the lens, just goes straight through. Then it goes into the higher orders, the 2nd, the 3rd, etc. Then it goes into the reflected modes, and it also goes into absorption. And Nilte has been able to get 94% of the light from the incident beam into the point spread function of the first order. And we're continuously working on improving this efficiency. If you look at the design of the single lens camera, it's made for 940 pixel illumination. It has an F number of 1.6, and it is characterized by having a high relative illumination and being stable to temperature change. And it is a telecentric design. The implementation we chose was to have a glass wafer with the aperture on one side and the Metalenz layer on the opposite side. And we will have an upgraded camera of this version at Photonics West in 3 weeks. So to conclude, it is possible to make a camera with a single Metalenz surface. And since the Metalenses are flat and matching the form factor of the sensor, which is also flat, it's possible to eliminate the field curvature aberration and the coma and the astigmatism. This is why you can have a performance which is equal to a refractive system with 3 to 4 lenses with a single meta-optic. Nilte also makes systems with multiple meta-lenses and hybrid stacks where we pair it with refractive lenses. And we're looking forward to servicing the industry here with fast prototyping. Thank you for your attention.
Thank you, Niklas. Now let's go to the question and answer session, and there is already Shenglin from Synopsys.
Yes, and I saw this. The focusing efficiency is very impressive. You can reach 94%. This is very impressive. I'm just wondering what kind of meta atom you used. I mean, what kind of material you based on?
So this is this was with pure pillars. So
I know it's what kind of material? Yeah, it's titanium dioxide or something else.
This is silicon on glass.
Silicon on glass. Okay.
Yes, but we also work with freeform meta atoms in order to squeeze the performance even higher.
So the operating frequency, operating wavelength is infrared, is that right?
This
Because
is 940 nanometer VCSEL illumination.
Okay, thank you.
Mm-hmm. And Shin-Sung from ANSYS, your question?
Yep. So the lens diameter you are showing here is millimeter scale, right? That's a
Correct.
large, I think. It requires a lot of meta elements. And so when it comes to actual fabrication of those kind of devices, what kind of challenges do you experience? And if you are, how are you overcoming those kind of problems? If you can describe that, that would be great.
So NIL Technology comes from, we were a mastering manufacturing company founded in 2006. So our history has been about manufacturing micro nanostructures with high precision. So that's where we spent the last sort of 14, 15 years trying to overcome these problems, trying to manufacture micro nanostructures with the highest precision. Our manufacturing method is based on electron beam lithography, which we use for the prototyping, and then we make masters, which we replicate by nanoimprint in order to manufacture in high volume.
Does that answer your question, Shinzo?
Yeah, kind of. So if you are relying on the electron beam lithography, which typically involves stitching errors, right? For example, if you are having that large Metalenz, how do you avoid those stitching errors from E-beam lithography?
So electron beam lithography is an art, and there are many tricks and strategies to overcome stitching, but I cannot go into that now.
Okay, thank you. Next question from Olaf, please. Eclipse Optics.
Yeah, hello, Niklas. Thanks for the nice talk. I was thinking the image you showed of the camera, it looks, maybe it's my screen, but it looks like there's a bit low contrast maybe. Is there an issue with the stray light or other?
So stray light, it's a good question. So if you look at this, what you have here, so the stray light comes from what you have in the 0th order and in the 2nd order. So stray light is directly linked to the efficiency of the optic. And this is why it's so important to maximize the efficiency. So the higher we can push it, the higher contrast we will have in the image. Then of course you can work with other means like baffles or other more traditional ways to minimize stray light. But I would say that minimizing the higher orders is the most important step.
Okay.
Okay, thank you. And now a question from Snapchat, Arseny.
Hi, Niklas. Thank you. Very impressive results on the efficiency. You mentioned that you plan to use nanoimprint lithography for the mass manufacturing. Does it mean that you will be then limited by high refractive index nanoparticles loaded imprintable materials for those devices, or do you plan to use sacrificial imprint layer to etch in some dielectric materials underneath?
The latter. So we're using the imprint just as a lithography step, and then it's etching to transfer into silicon or other materials, depending on what wavelength you're targeting.
Thank you.
Thank you, Arseny. And the last question from Fraunhofer IOF, Robert.
Yes, thanks. Question about the field of view of this camera. You said 1.6 f number. Can you tell a little bit more what's beyond possible? What are the limits here, especially thinking of efficiency of creating incidence angles, etc.
So field of view is something that you can go to very high field of views, and that it's interesting. It has to do with the fundamental property of metalenses to bend light very steeply. There is one article in Nature where they demonstrated, I think, 178 degrees field of view. We also verified this in CMAX that it seems to work okay. When it comes to the F number, you will take a hit on the MTF if you go down below 1.6. We have looked at going down to 1.4. In order to go beyond that, you need more complex. You need more than one lens.
Mm-hmm.
That is certainly possible, and it seems like in general it's a trend that when you introduce meta optics into the refractive system, you can reduce the F number more than what you can with just the refractive lenses.
And then so you would, as a possible solution would be 2 metalenses or a combination hybrid metalens plus refractive.
Exactly, one of those.
Okay, thanks.
All right, and if there is no more questions from the audience, I suggest thank you, Niklas, again for the presentation, and
Thank you.
we'll move ahead. And the next talk is given by Rob Devlin, the co-founder and the CEO of Metalenz that we already heard about today. And he will show us about the meta optics and transforming the sensing and moving optics into the semiconductor foundry. So please, Rob, whenever you're ready, the floor is yours.
Perfect. Can you see my screen okay?
Yes, you're good to go.
Great. Yeah, so I wanted to thank the organizers for inviting me, and it is definitely great to see all of this interest from industry. I think it's a sign that meta surfaces are more than just an academic curiosity and really are impacting real applications in industry now. And what I'll talk about today is how we've taken at Metalenz meta surfaces from the lab, transitioned them into the semiconductor foundries, and are now shipping them and commercializing them. And I'll talk a little bit about as well some of the future products we have where we're seeing enabling new markets, new applications with some of the new forms of sensing that meta surfaces can ultimately bring to mobile form factor, mobile volume, mobile price point for the first time. And so just a little bit about the company Metalenz. We spun out of the Capasso group of Harvard University, where the foundational research on these meta surfaces was carried out back in 2016. And really, we're focused as a company on the design of meta surfaces, new applications of meta surfaces. So we are a fabless semiconductor company. Instead of being a fabless electronics company, we're a fabless optics company. And this really lets us focus specifically down on optimizing designs and new applications. And at this point, we're about 30 plus people here at Metalenz. And really, again, a lot of that focus is on the design tools, and making the best meta surfaces for applications. And as far as the manufacturing goes, we now have multiple semiconductor partners that we've worked with in actually bringing up the process to make our meta surfaces at scale. And then down below, I list some of the investors in Metalenz. So we have a number of different investors. Many of the companies are even here on the talk today, like Applied Materials we've heard from. And this is really a number of companies from the semiconductor industry showing the interest of taking optics and moving it into the semiconductor foundry, and really the impact that you can have by doing that. So I think we've heard quite a bit about how meta surfaces work, and I think most folks are now familiar with that. Just a few things to touch on. Niklas also highlighted this quite nicely, that to me, essentially the critical aspect of the meta surface is this ability to put multiple functions into one surface. So you can very nicely replicate refractive type functions and diffractive type functions into the same layer. But also you can then control things like polarization, which I'll talk about a little bit later on, where you can actually put completely different functions into one single layer and essentially be able to switch between them. But also the meta surface's ability, if you contrast this to the refractive lenses, it's this ability to control all of the information in light. So you can access polarization, you can split out wavelength. But one of the biggest caveats is the technology as it exists today, if you're trying to make a good lens or a good dot pattern projector, really is focused on narrow band wavelength still. The full broadband meta surface, there have been some demonstrations, but from an efficiency, performance, and manufacturing standpoint, isn't quite ready for mass production. But there's a huge market for these narrowband type applications, some of which we've already heard about: LiDAR, 3D sensing, general biometrics, autonomous driving, and so on. And that's where we really focused at Metalenz to get this into market, is on those narrowband 3D sensing applications for the near infrared. From the manufacturing side, again, as metasurfaces were conceived, the idea here was that you could use existing semiconductor foundries, existing semiconductor processes, an industry that is quite mature in order to mass produce these metasurfaces. There's a lot of technologies, photonic technologies, that have shown great promise, but haven't had the manufacturing scale or the manufacturability. Metasurfaces really allow you to make this at scale through existing foundries, which is why we can launch at such large volumes with a new technology. To just take a quick step back, metasurfaces, the concept really didn't just come out of nowhere. It goes all the way back to Fresnel lenses, diffractive optical elements, whether that's multi-level DOEs, binary DOEs, and especially from these phased antenna arrays. Essentially, you can conceptualize metasurfaces a little bit like a phased antenna array at optical frequencies. The first demonstration generally of this was using these resonant structures in order to collimate light coming out of a laser facet in the Capasso group back in 2007. And then in 2011, it was this more generalized concept of being able to get full control of polarization phase from a single semiconductor layer in a process that was compatible with, again, semiconductor foundries. The way that we see Metalenz really impacting the overall optics industry, if you take the move from glass to plastic lenses, what this allowed you to do was really to take a form of sensing that was previous niche and move it to mass production by making lenses smaller, cheaper, and really allowing them to proliferate everywhere. As you look now, there's an even bigger explosion of cameras and sensing devices because of autonomy, because of biometrics. And we see Metalenz enabling this in terms of continuing to allow complex sensing devices to get smaller, simpler, cheaper, better performing, but also introducing entirely new functionality, again, which I'll talk about a little bit later on. And then the other way we see metasurfaces really impacting the industry is by moving optics into existing semiconductor foundries. So Gauthier from Applied Materials had a really nice presentation about manufacturing metasurfaces on 300 millimeter wafers. So what we can do now is move optics into the same foundries, making the electronics, and using deep UV lithography, really using that existing infrastructure. So on a single 12-inch wafer, you can now print something like 7,000 to 10,000 metasurfaces. And what we've seen is really by leveraging that mature industry, we can actually get very high yield right out of the gate from our first products as well. So we see something like 97% yield on the first products that we're putting out there because we're using that existing infrastructure. So if we take a look at what metasurfaces generally do for optical systems, because we're not just looking to replace one-to-one a single refractive lens, we're looking to replace a full stack of refractive lenses and then derive more benefits at the system level. And really with metasurfaces, you can reduce the complexity of these sensing systems. You can shrink the form factor in many cases. And ultimately, you also improve performance. This is one of the key features, is that when you're making this simplification, you're not trading off against performance. In many cases, you can even improve the overall performance. So from our first generation of products, one of the first things to highlight is a dot pattern projector. If you look at something like the iPhone doing structured light in order to build up a 3D image, on the transmit side, you have a set of 30,000 dots that gets projected out onto your face. Again, because with a metasurface, you can put these multiple functions into the one layer. What you're able to do is actually take the refractive lenses, the diffractive optical element, and put this all into the one single semiconductor layer. You can also achieve very wide field of view in this case. So you can achieve up to 150-degree field of view with this particular projector. And so it allows you, again, to simplify this 3D sensing system that has been rather complicated and difficult to assemble as well. You can also make lenses. I won't dwell too much on this. Niklas has already talked about making lenses and cameras using a metasurface. So this is a product we originally introduced back at CES in 2020. of looking at metasurfaces on the imaging side. And as Niklas pointed out, you can essentially get this single metasurface lens. And really, again, you can impact system level metrics, not just replacing one lens to one lens. So ultimately, if you look at how much light you're getting onto the image sensor, you can get more light with the metasurface solution. So again, whether it's on the transmit or the receive side, metasurfaces bring significant improvements and significant performance in terms of the dot size that you might get from a transmit, in terms of the amount of light you might collect on the receive side. And then there's also a whole bunch of different module level advantages that you get when it comes to assembly, when it comes to performance, and so on. So this is a cross section from Yole of the iPhone 12 LiDAR. And so both on the transmit and receive side of this system, metasurfaces and what Metalenz can do really gives you substantial advantages at the system level. As I mentioned, this has now been commercialized and we're shipping this in market. And this has been in partnership with ST Micro. They make this flight sense module. We've worked with them, and in their foundries, they've brought up the process to make these metasurfaces. So this is now something that has moved from the lab, is shipping in real devices today in ST's flight sense module, and now is impacting directly consumers. It's being shipped into consumer devices, and no longer just in the lab. It really is being used in many different use cases in order to improve that overall performance of the 3D sensing solution. But more than just taking existing solutions and simplifying and improving them, metasurfaces allow you to then access additional information, new information that, especially at mobile form factor, has historically been very difficult to achieve. And one example we have is what we call Gemini. In this case, what we're able to do is actually have two completely unique and independent patterns coming out of a single projector. So in many 3D sensing cases, you're often trading off in terms of the performance or in terms of the use case or application that you're targeting based on whether you're projecting a dot pattern or a flood illuminator. With a metasurface, because you can encode polarization information into that same single semiconductor layer, using that very simple process in order to produce these, you can now actually have a single module that will project two different patterns depending on what polarization is incident on the optic. So everything is static, no moving parts. You're just electrically switching polarization and now getting more for the single module that you have for the single illumination module. And then the other place where we see bringing new information to mobile form factors for the first time is in polarization sensing. So we have our polarized product, which again leverages this ability of metasurfaces to actually parse and split out the polarization information. So if you want to traditionally capture all of the polarization information of light, the full Stokes parameter, you may need a very large tabletop camera, but with a metasurface, we can now shrink that down to mobile form factors, mobile price points, and really allow polarization for various applications to proliferate. So we now have evaluation kits that we're sharing with key partners for this polarization sensing that allows you to bring this new form of sensing to these markets for the first time. And really, again, this is the exciting aspect. When you look at metasurfaces, what they provide, it's taking these very complicated optical systems, improving, shrinking them down, reducing the complexity, and then allowing them to fit into form factors, price points, and scale compatible with mass markets. And so just to finish up, I think the other really interesting aspect of what metasurfaces allow is, again, moving optics into the semiconductor foundry. So we move away from the traditional optical supply chain in many of these use cases where you have multiple different lens companies, a foundry that makes a sensor going to the module integrator. Now what we're doing is making the lenses, the DOEs in the foundries that are making the sensors and the electronics, still in many cases using a module integrator. But over time, you can even see, much like with wafer level optics in the past, this promise of now having the full integration of optical modules in a single supply chain. And this is a really exciting aspect, I think, for metasurfaces, and definitely interested in looking at further use cases that we can get as we introduce some of our new products as well. And so with that, I'll finish up and Just of course make the plug that a startup will always make, which is we're hiring. So if anyone here is interested, please reach out, and we have lots of open positions and lots of interesting things going on here.
Thank you, Rob. You do have lots of interesting things going on there. And let's go into the question session now. Xinglin from Synopsys, please go ahead with your question.
No, I don't think it's me.
Okay, maybe
Sorry.
your hand is still raised. All right, then Reto from Materials Optics, please.
Yes, hello, thank you very much. Very good talk. I was interested, I reckoned in these talks there were already different approaches described or presented how to manufacture metalenses. On one hand side, DUV, and from Nilt we before heard nanolithography. Are there any pros and cons for one approach versus the other, or limitations in one of the approaches to manufacture those optics?
Yeah, I think it very much depends on what you're trying to make in the end, the scale of what you're trying to make, the volumes that you're trying to ship at. For us, really, as a fabless company, the thing that matters the most in terms of when we go to mass produce this is getting the best performance, the best yield, and a scale that can meet customers' demands. And as we looked at the different approaches, what really gives you that is doing this in deep UV in the existing semiconductor foundries. Again, this is a very mature industry. If the sizes are compatible with deep UV lithography, it's going to be very difficult to get the type of control with other approaches, as we've found as we've investigated this. So really it's coming down to yield, performance, and then the scale. If you're doing things in really large area, in many cases, nano imprint may be a better approach. But generally, again, for us, we're just looking at someone to manufacture the parts since we're a fabless company. And as we went through, there was nothing that was going to get us the type of performance, the type of scale that would meet customer requirements other than doing this in existing semiconductor foundries. It's already a mature industry.
Thank you very much.
Rob, I'm wondering, do you experiment with various materials? And maybe is it possible to use polymers?
What was the last part of that?
Yeah, if you experiment with different materials when producing meta surfaces, and also in particular polymers can be used for that.
So yeah, we also have looked at a variety of different materials. When we spun out of the Capasso group, we were primarily focused on visible wavelengths, and a lot of the demonstrations we had done there was invisible. So we actually worked with titanium dioxide back in the Capasso group. That was for visible applications. For the near infrared sensing, 3D sensing, where we're commercializing this, silicon is the natural choice from a performance perspective, from a cost perspective. So really for the different wavelengths, we look at different materials, but everything we've done for products that are now commercially available, that's in silicon just because of the performance and the cost.
Okay. Another question from Snapchat, Arseny.
Hi, Rob. You and some previous speakers mentioned that the current application of metamaterials is focused on the single wavelengths. What are the challenges of creating meta optics for multiple wavelengths or broadband, and also for what are the challenges of creating meta optics for imaging applications, like not a single wavelength, but a broadband spectrum?
Sure, that is a great question. So, there have been demonstrations from a variety of different groups, from Capasso group, from groups at Caltech, and so on, of actually being able to bring all of the colors of light to a single focal plane with a metasurface. So this is possible with metasurfaces. The biggest challenge ends up being that you start trading off against efficiency. So, you're going from the 92 to 94% efficiency that you might get with a single wavelength, and now you're trying to do this over broadband. Even at the wavelength where you may have maximized the efficiency, there's often a roll-off in efficiency over that broadband. So you might be getting, I think, in some of the best demonstrations out there, 50% of the light actually getting to the focal plane. And so that's really one of the biggest challenges is efficiency. The complexity of the structures also increases if you go to these broadband. So they're not just nice, simple pillars. You often need a more complicated set of meta atoms in order to actually get broadband. That is a case where, again, I think things like nano imprint can be quite interesting if you're trying to achieve these more complicated structures. But really, it's that trade-off in terms of efficiency and performance as you go to broadband that still hasn't really been overcome. And I think, again, if you're not getting 99.5% efficiency at the narrow band, it's going to be really hard to say that you're going to get that at the broadband. So when you start thinking about imaging applications too, for visible imaging, there's always, in most use cases, a person that is looking at the image. So any form of stray light, anything that is going to be slightly off is going to make the camera not as appealing. But if you look at the narrowband applications, you're now looking at maybe a machine vision type of application where you have other metrics that may be more important than just the full perfect Instagram photo you're trying to post, or Snapchat photo for that matter.
Thank you.
That's a good example. And the last question from Fraunhofer IOF, Robert?
About the sensor or the product you have, Gemini with the two possibilities to work, whether as an dot projector or whether as a diffuser. So you said that you can switch the polarization. Can you elaborate on that? And what are the differences? Do you use then different light sources, or is every time the same light source? Coherence, is there a problem?
Yeah, right. So we actually and we made an announcement with this with our partner Trump Photonics as well, where we've been working with Trump on, they actually produce a VCSEL array where they can switch back and forth between different polarizations electronically in the VCSEL array. So they have a VCSEL array that can now have two different polarizations electronically switchable incident on the meta surface. And so the way that we end up designing the meta surface is for polarization A, you get a dot pattern. For polarization B, you get your diffuser. And then in this way, you can switch back and forth using the actual VCSEL source and that electronically switchable polarization.
Okay, thanks.
All right, if there is no other questions, Rob, we thank you again for a beautiful presentation and sharing so many exciting applications with us. And so, of course, it was amazing to see how meta surfaces can alter the wavefronts of light. And actually, one of our guests today is also a specialist in measuring these wavefronts, and that's Ines here from PhysiCs. Ines, would you like to share a quick message with us?
Yes, of course. Hello. So I'm going to share my screen. Can you see my screen?
Yes, you're good.
Okay, so I'm Inesia. I'm a technical state engineer in PhysiCs. So PhysiCs is actually a company specialized in manufacturing high resolution wavefront sensor, which is actually based on the own patented technology, which is called Gauthier interferometry. So today I'm going to do a quick summary about how with a wavefront sensor we can actually characterize optical metasurfaces. So the goal is actually in the photonics metasurfaces is that it are optics with phase shaping properties that are mainly dictated with geometric parameters and nanostructure arrangement. So to characterize them, we actually need metrological tools that are achromatic to actually match the design wavelength of the metalenses, for example, and non-polarization dependent. For example, Metalenses who has optical properties who depends to polarization. So for that, PhysiCs propose the SIT4 ST8 that you can see here, wavefront sensor. So the advantages is that it's achromatic, it's non-polarization dependent, it's also high dynamic, and it's easy to integrate since it's small, has a camera vibration independence. So with this wavefront sensor, the outcomes, actually we can characterize, control, and confirm the metasurface manufacturing process. So as you can see here, it's possible, for example, to get the phase intensity piston of the airy metasurface or PB metasurface. We can also control the optical functions as measuring the wavefronts, having curvature properties, having PSF and MTF, or having the naked aberration of the metasurfaces. So some application example that we can do with the wavefront sensor, we can, for example, for PB metalenses, we can check the polarization dependent of the Metalens focal length, as you can see here. We can also characterize phase vortex, so we can also characterize beam deflector. So thank you for listening to me, and if you have any questions, don't hesitate.
Okay, thank you, Ness, for your quick message. And now back to the agenda. I will introduce the next speaker, who is Patrick Schuster. He's a process engineer at the EVGroup, and he will tell us about the Metalenz manufacturing using nano-imprint lithography. Patrick,
so
whenever you're ready.
Yeah, many thanks. Many thanks for the introduction. You should now, yeah, see the screen. So as said, many thanks for the introduction and also for organizing this event today. My name is Patrick Schuster. So I'm a process technology engineer at EVGroup. And today I want to introduce you into the nano-imprint lithography and also how to use this technology for manufacturing, for example, metalenses or metasurfaces. So first of all, EVGroup is a supplier of wafer processing equipment for the nanotechnology, MEMS, and semiconductor markets. And we were founded in 1918 by Mr. and Mrs. Thalner, and we currently have over 1,200 employees worldwide. The headquarters and also the manufacturing of all our equipment is located in Austria, but we do have subsidiaries all around the world. And our main or core technologies is the wafer bonding and debonding, photolithography, so lithography with standard photomasks or even maskless exposure, and the nano-imprint lithography. The NIL technology at EVG is divided into two processes. So first of all, we have the step and repeat mastering service or process, and we also have the NIL technology, which is then used for replicating the final devices. So when we first start with the mastering, we typically get a single die master like this. So this is an etched quartz mask with Metalenz structures, and it's provided by Topan Photomask. And we take this master template and create here a template for our EVG 770 step and repeat system. And this template will be then used for imprinting the single die, which you can see here in the master, several times on a new carrier wafer. And this will be repeated until we have a fully populated step and repeat polymer master template in the end. So, and the purpose of this is to create a cheap process and a process where you have, let's say, or to not have a risk, to damage the original master. So while processing, for example. And while we creating this step and repeat master template, we achieve a very stable pattern fidelity. So in geometry, size, height, and so on, all over the replications from die number 1 to die number 3, 4, 6, etc. And this is, of course, needed because if you're thinking about high volume manufacturing, all the lenses should have the same optical performance. And that's why a stable pattern is very important, and also that there are no missing structures inside of the Metalens itself. After that, so when the step and repeat master is created, we take this master and coat a working stem polymer on top. And with this coated master, it will be loaded into an EVG SmartNIL module. This can be either be a standalone tool for R&D purposes, for example, or even high volume manufacturing. and we create a negative polarity working stamp from this fabricated step repeat master, so which we have created in previous steps. This working stamp will be then attached to a imprint substrate where we have coded like a anneal resin. This can be a standard refractive index, high refractive index, or low refractive index according to the customer's needs. And after curing the polymer, we detach the working stamp, and then we can create with this stamp multiple imprints. According or depending on the structures, you can create, for example, one batch of wafer like here, so 25 imprints or even more. The main benefit is that the working stamp manufacturing and the imprinting is performed in the same equipment. So we do not have to exchange any hardware, except, for example, the imprint chucks when you want to imprint on different sizes of wafers. But the working stamp is mounted inside the tool, and we do not unload or cause any risk of contamination or damage of the stamp then. And also for the imprint fabrication, it's of course important that the very first imprint has the same quality as the 25th or the 50th imprint, because otherwise you will have different optical performances, of course. And when we check, for example, this batch or 25 wafer, where we have imprinted with one working stamp, you see the pattern fidelity is really stable. So we have checked different pillar geometries. So here, for example, fully round pillars, but we also have checked like we call it donut shaped. And the pattern height is really stable across these imprints. So with the smart anneal technology, which is for the high volume, we are enabling a high wafer to wafer pattern fidelity. And we also can create the many different lenses in a single shot at, for example, a 300mm wafer, 200mm wafer, or square shaped substrates, just with one smart anneal imprint process. So in a summary, nano imprint enables a technology to create a wafer level based manufacturing of different structures, metasurfaces, metalenses, and so on. And we can do this from a single die replication to even, as said, whole module on a 300mm or even Gen 2 substrate size. And the smart anneal technology is very flexible in terms of shapes and sizes. So we're not limited, for example, just to round pillars. We can also do rectangular shapes or even with holes inside and so on. So here it's very, very flexible. What we can do for you. So first of all, we can perform live demonstrations in our clean room. So we have the capabilities or the tools inside of our clean room to show you the technology, the equipment, and so on. And we also develop the processes in together with you. So you say what you need or what's the requirement for your final device or imprint, and we try to optimize the process for and at our equipment as much as possible. But we also are interested in, for example, joint R&D projects, or we can also provide some pilot line production in meantime when the equipment is, for example, manufactured. What we're looking for, first of all, materials, because without materials we cannot do the imprinting. This is a very beneficial thing for the imprinting. We're also looking for new mastering partners. So we have a lot of different mastering partners such as Topan, but we're also interested in new techniques, technologies, and so on. And the main thing what we're looking for is, of course, design and new customer challenges, because we also want to improve and we want to improve our technology step by step. In the end, of course, if you're interested, you can ask the questions here, but I just want to take the opportunity. We currently are launching a white paper in collaboration with Topan. So either you can follow this QR code or the link down below. But as said, I'm open to questions and want to thank you for your attention.
Thank you, Patrick, for sharing your capabilities and your vision. The session is now open for questions. Do you have any questions in the audience? Yeah, Shenglin from Synopsys, please.
Okay. Two very simple questions. One is the fabrication tolerance. The second one is about the lifetime of your stamp. And what I heard is you had to clean it after a while, after a number of uses.
So maybe first the first question. So tolerances, it's always depending. So in terms of mastering or in general the smart new replication.
Of course, the final product. Yeah.
Okay. This is highly depending on the material combination. So this means the working stamp which we are using. So we are offering, for example, our EVG working stamp materials, but also in combination with the imprint material, because polymers have a certain shrinkage. But the good thing is the shrinkage is always the same. So once we have, for example, done a few imprints and qualified the shrinkage for all of these imprints, you can then compensate this into your master template. So at this loss of height, for example, or diameter, and then you can adjust the process to your, let's say, geometries or sizes which you really need. So there's maybe then one iteration, but you can compensate the shrinkage then. And as said, depends really on the material combination as well as on the geometries and also the size of the structures. But typically with our EVG material, for example, we say 3 to 5% material shrinkage. And for the second question, sorry, can you repeat again?
Basically, the lifetime. I mean, what I hear is you had to clean it, the stamp after a while. Yeah.
So that's the benefit actually of the SmartNet, because we have a polymer stamp, and this is fabricated really in a few minutes. And once, for example, the lifetime is, or the working stamp comes to its lifetime end, you can fabricate a new one, and this is really can be easily exchanged and so on. And the lifetime itself also depends then again on the material combination and also the structure geometries. But typically our goal is, for example, minimum 25 wafers with one working stamp. So one batch with one working stamp, but we also have shown that we can even do more imprints with one working stamp. But for example, for lines in space, for gratings, the lifetime is probably much higher than for, or binary gratings is much higher than for slanted gratings. But this needs to be tested then.
Thank you.
Thank you, Shenglin. And another question from University of Southampton, Kai.
Hello, just curious regarding to the, I would say the manufacture speed of these tools. It looks like it's automatic tools. So how many substrate it can handle per hour? Thank you. And what's the minimum features, by the way?
Minimum features, so we can go below 50 nanometers, definitely. Then it's depending again if it's pillar structures, if it's grating structures or so. But let's say 30 to 50 nanometers should be feasible. And the speed of manufacturing is also depending, because when we attach the working stamp, the capillary forces are filling the structures actually from the working stamps, so we do not apply the actively force. And depending on the structures, this takes some time, but you can estimate imprinting process between a few seconds to a few minutes, but for bigger structures, for example, then it takes longer.
Thanks.
What is the typical wafer size you work on, Patrick?
We handle between 2-inch up to 300 millimeter, so everything's possible here.
Okay, that's a lot of capability. Okay, thank you very much. If there is no other question, is there another question? Zhengli, maybe more photonics, please.
Yes, thank you. I have a question about the residual layer of the resin of the curing. To make the Metalenz, you need to remove the residual layer, and how good you can control the thickness of the residual layer.
So typically we go with a residual layer between 20 and 30 nanometers, because if you want to etch this into your substrate, of course, it needs to be as low as possible. But if it's too low, you might get, for example, adhesion issues for very complex structures. The good thing is, so we can control the residual layer because the structures itself need a certain volume of the resin. And with spin coating, we can achieve a very uniform coating of the needle resin. So between, let's say, 30 nanometer resin layer up to a few microns. And everything which is not consumed by the structures, this is then just the residual layer. And you just need to subtract or the remaining thickness, let's call it that way.
Yeah, okay.
This
thanks.
would be spin coating, but there's also, for example, the opportunity to perform inkjet for the needle resin. So to make, for example, grayscale prints and so on. And then it's also tunable.
Yeah, thank you.
Thanks.
Okay, thank you for all the questions. Thank you, Patrick, again for the great presentation.
Thank you.
So EVG is of course famous for fabricating all kinds of micro optics and on the wafer scale. And my colleague Jeremy is actually also has a message that is very relevant for this topic. Jeremy, would you like to say a few words?
Yeah. Thank you very much, Ivan. Yeah. So a few words about Fabulous. Fabulous is a pilot line, which is a European one-stop shop for the manufacturing of freeform micro-optics, offering accelerated innovation and production cycles from prototypes to piloting and large volume production. And actually, this project addresses several fields like AR, VR, as you can see, measure and displays, transportation, as well as security, automotive lighting, for examples. And this year, so in 2023, we will have 3 open calls in March, June, and November. So we, of course, invite you to apply if you are interested by this opportunity. And if you are interested or need more information, I really warmly invite you to contact Jessica Van Eck, this director of Fabulous, who is in the room today, or me. We'll be pleased to give you more details regarding Fabulous. Thank you. I will put the email of Jessica and my email in the chat. Thank you very much. Thank you, Ivan.
Yeah, you're welcome, Jeremy. And back to the agenda. So the next presentation is given by Lieven Penninck, who is the founder of PlanOpSim. And they're software experts, and they present a view on the opportunities and challenges for the design of metalenses and metasurfaces.
Yes, thank you, Ivan, for this introduction and for the opportunity to switch gear here a bit from the different manufacturing approaches and great achievements that have been made into the further opportunities and challenges still for design of metalenses and metasurface. So I'll be presenting some of our viewpoints on that. So what do we see as the current limitations? In 3 aspects, these are actually to make the design fast, integrated, and reliable. First of all, there is the integration to system level. So we've seen quite good demonstrations already of single metasurfaces here. If we want to fully exploit all the possibilities for manipulating the light, we have to get these metasurfaces into systems consisting of many different components. And that means we need a link between the wavefront scale and the ray scale that takes fully into account all the possibilities that the metasurface has. If we also look at the sizes, even here for 40 millimeter Metalens, which most of you would agree is a quite big Metalens, this is very difficult to model right now. So we need to have design tools for larger area and for faster simulations, and that are simple to use. Currently, it's mostly done by PhDs. Ideally, a bachelor in optics should be able to do this, and we should improve all methods for getting the system level yield as high as possible, going from just nominal designs to more and more robust designs. And in the next couple of slides, I will be presenting our view on these challenges. So PlanOpSim is a service and software company. We make a software solution to make metasurface design as easy as possible. And we actually provide our customers with full support along the design cycle, from the concept phase where you are determining whether a metasurface is actually the right solution for your application, down to modeling systems and then using our tool to model from the nanostructure to the component level down to validation and fabrication. So to look at a little example of system integration, we take here a classical example of a fiber coupler that we optimize using idealized metasurfaces. What we have done here and what's very much needed in order to really use the metasurfaces is to inform the ray tracer of all the different limitations, for instance, for dispersion and polarization control, with information obtained by the nanostructure solutions, which are the limits there in terms of time bandwidth, as well as higher order diffraction, which was talked about already before. And this lets us do a cascaded co-optimized design, either of what we call a meta system here, where you have two meta surfaces working together, or of a hybrid system where you have meta surface combined with spherical lenses. Because even though meta surfaces have great possibilities, there's also several limitations, as we mentioned before, for instance, in terms of the diffractive chromatic effects of the flat lens itself. And if we compare that, we can arrive at a system, as Rob already showed earlier, which is drastically smaller and simpler, which potentially, if we control all aspects well in the future, can have 27% lower losses compared to the conventional solution. But this requires a coupled design where the nanostructures inform the system design and the ray tracer, as well as a system design that can fully exploit these in terms of polarization and dispersion control. That brings us to the next bottleneck. For a lot of applications, we need larger metasurfaces going from few millimeter to centimeter scale and more. And if we look then here on this lens, the largest feasible simulation area using just full wave solution corresponds to this little green dot here. If we use multi-scale approximations, as we do here in PlanOpSim and as well in various other softwares, it's actually extended, but still 50 to 200 times smaller than the actual lens size we want to create. And the biggest bottleneck there is the poor scaling of the electromagnetic solvers. And if we look at a typical project, then we often need 10,000s of structures to be optimized, either parameterized or in a free shape system. This needs to be drastically improved in speed. That time that we spend there calculating, you can have a supercomputer or whatever you like. Generally, it's limited by how many calls to the electromagnetic solver we need to do and how many loops we need to do over using the optimization algorithm. So to get out of this obstacle, we need to have the fastest, the smartest optimization algorithm and the fastest solver. And there are two approaches that you see there and that we are implementing. And that's on the one hand using inverse design with various optimization algorithms. You see some that we have benchmarked here. Typically, you can reduce the number of solver calls that you need from a bit more than 1,000 to a couple of hundred calls. And combining that, we call a surrogate solver. That's a pre-trained neural network that replicates the full wave solution. There's a requirement there that you need a large enough training set in order to do that. And you need to stick to sufficiently similar configurations. But when you do that, we can get very good reproductions of the full wave calculation, but in a much faster time. And the good thing about these approaches is that they are essentially orthogonal. We can combine optimization with the neural network solution. And if we look at that then for a typical metasurface design project, where a brute force calculation might have taken 20 hours, combining the inverse design with the neural network, we can actually get that down to a couple of minutes or 500 times faster. That's already a great step. Where we want to go further in the future is to bring this into widespread use, but also increase the size that we can model on so that we are not limited to just couples of meta atoms. That brings us then into a final part that will become more and more important for design tools in the future, and that is the possibility to do design for manufacture. So the failure modes of metasurface are actually a bit different from what you would see in classical refractive lenses, and therefore Monte Carlo methods and sensitivity analysis needed to find what are the critical parameters and thresholds. We've seen some already on the component level, but we also need to understand how these play into the particular system that you're designing, and then to be able to tolerance the system and mitigate these errors on the system level as well as on the component level. For that, we've developed tools as well. So you see here in this plot, for instance, are 25,000 individual lenses simulated in order to find out what their sensitivity is to sidewall angle, changes in height, structures being moved. I can really talk for a long time about all the different design options as well as limitations, but I'd like to ask you to contact me for that in order to discuss in depth about your project or to ask a question here. Thank you very much.
Thank you very much for the presentation, Lieven. It's now open for questions from the audience. Just use the raise hand button if you have something on your mind. And I was wondering, Lieven, I mean, it's very clear what you present, to what you can offer to the other members. Is there something that the community can help you with in the developments or maybe testing your software?
Well, we've thoroughly tested our software. Now, what we're really interested in now is to link this software to the various ways of fabricating. So if there's what we see as a big next step for meta surface design is to have design rules which can be validated already in software, so that a designer can essentially make sure his design is well within manufacturing limits before sending it off for any sort of real-life expensive testing.
Okay, I see. Okay, there's a question from Huawei. Gabor, please.
Yeah, thank you. You presented a very impressive speed improvements, the combination of a neural network and a genetic algorithm. And you mentioned that the neural network will work only if you have a very, how to say, similar design. So you have a parameter that you want to run or scan or optimize, and the design will not change significantly. In this case, the trained neural network will work. Do you have a more rigorous definition on how similar the design should remain?
Yeah, we can go a bit in depth about this, but in general, you have to stick within the same spectrum and material set, as well as generally the same type of structure in order to get the best results. I expect with the rapid improvements in AI that this will improve in the future, but this is, as far as we can tell, the current status.
You also mentioned that you need a trained data sets, which I believe is pretty difficult to obtain. So could you please elaborate more on that? How you create your training data set?
Well, actually, the data set is created with the full wave solver in order to get a large set. And this is actually maybe more clearly what I meant before, that if you're doing just one project and you're pre-training a data set, the amount of data you need to generate in order to then get these speed improvements is longer than it would take to calculate the whole project. So for just a one-off project, it doesn't make sense.
Okay.
But if you think about this, and this is where, for instance, the move to Foundry type of services is very interesting. If there's a standardization there, we can get designs very fast if it's pre-trained on the types of structures that are anyway required for manufacturing. So this is kind of a false limitation in some cases.
Okay, excellent. Thank you. It's clear.
All right, and the last question coming from Snapchat, Arseny.
Hi, Lieven. One of the asks from the potential end users of the metamaterial optics is whether we can redesign the whole conventional system with conventional optics, replacing optical elements with the metamaterial. So, for example, if I want a time of flight sensor, which was already presented in this meeting, can I just is it something which is possible with your software right now? So I just say, this is my conventional optics. Can you replace it with metamaterial optics? Or is it something which could be done in the future and be potentially useful for people doing this metamaterial lenses designs?
Yeah. A straight one-on-one replacement of a conventional system, an existing system with a meta system will not be possible in my view, because the physics are different. Essentially, a meta lens is a diffractive lens. The chromatic behavior, for instance, of a refractive lens and a diffractive lens are opposite. So just directly replacing them will only work in a very narrow spectral range. What is, in my view, the future is a hybrid system where the advantages of the meta lens and the refractive lenses are combined in order to get to more broadband solutions and introduce these new features such as polarization control.
But then if I'm trying to design not a single optical element, but the whole device, so if I know it's a time of flight sensor, is it possible just to say, like, I want it now with the meta optics and not conventional optics, and set up performance targets and get a set of optics for the some standard final device?
So this kind of design will require a combination of ray tracing in any ray tracer of your choice, together with, I've shown it just a bit before, the nanostructure libraries that we can provide. This will be a cascade design back and forth between the system level modeling, which of course in real engineering still connects then to mechanical, thermal, and so on, and the nanostructure, nanocomponent modeling that's in our software.
Mm-hmm. Thank you.
You're muted, Lieven.
I'm sorry. So thank you very much indeed, Lieven. And with this, I suggest that we pass to the last presentation of this session. Maryvonne Chalony, the application engineering manager at Synopsys. She will talk again about the software tools for the meta optics designer, fully automated commercial tool for meta surface optimization. Please, Maryvonne.
Thank you, Evan, for the introduction. So, yes, my name is Maryvonne Chalony, and today I will introduce to you the Meta Optics Designer. It's our new modules, fully automated tools for Metalenz, Metasurface with inverse design capability. So, and I'm working at Synopsys, so it's a US company dedicated to optical. So, I'm from the Optical group, so dedicated to provide to our customer optical design software. Yes, so let's start with a bit of background, but it's exactly what was referring from the speaker before about the design flow used for Metalenz surfaces. So typically people are using ray tracing optimizer to extract the phase profile of the optics. On the other side, they are using electromagnetic simulator, either RCWA, FDTD typically, to generate the meta-atoms library. And having these two pieces of information, we can combine using a script the information in order to generate the layout of the Metalenz. And then having this Metalenz, so this layout, we can go for verification of the optical propagation using either so Maxwell solver simulator or ray tracing software, beam synthesis propagation. So there is a kind of diversity with pros and cons for each of them in terms of verification. So that's what is used to be done over the past few years. And now on our side at Synopsys, we released last September Meta Optics Designer. So it's a fully automated tools with inverse design capabilities. The idea is really to bring all the complexity of the design of Metalenz inside the software and let designer having different level of expertise to create novel Metalenz design quickly and easily. The target is really to have shorter design cycle and to reduce the cost of this design process. Really at the high-level overview of these tools, so typically we have an optical system with an incident field, optical combination, one or several metalenses, maybe also combined with refractive lenses. So some people was calling this type of system hybrid system. And at the end, the designer want to have a specific output, a desired field at the focal plane. And the engine will work and optimize the entire layout of the Metalenz or the several Metalenz inside the combination to reach as good as possible the optimized output in spatial distribution, and also targeting to have the best power absolute focusing efficiency for this design. It's based on inverse design. So I will mention it later in one example, but we have done a lot of validation using FDTD and engine for the propagation validation of the simulator. And I would like to mention it's a really efficient engine. I will show you an example where we have really high efficiency in terms of time of simulation. Let's go back to the inputs and outputs required. So the inputs required from the user. So a user will have to specify a set of lenses for the optical system. And again, it can be one Metalenz, several metasurface. It can be a combination with refractive lenses, curved lenses. And we have also to provide the BSDF database, what we call the MetaAtoms library for each of these surfaces. Then we have to define what would be the target. So either the hairy spot for the specific wavelengths at a specific distance of focal distance. It can be also just an image at the focal distance as a plane. And then MetaOptics designer will do the optimization using inverse capability. Agent fields method is used behind to provide the optimized image and generates the equivalent, so the layout of the metasurface to get this image. And all the parameter definition of the meta-atoms will be provided from the software. Few design example to illustrate the capability of MetaOptics designer. So let's talk about the fisheye Metalenz. So it's well known to be quite challenging to reach this type of design. So on our side, we were using silica based materials, square shape for the nanostructure, the meta-atoms, and then we we explicitly had the targets for different angle of incidence. So in terms of the focal distance and the position of the focal point after optimization. And so what we can see on the right, we can see at the top the visualization of the propagation of the beam. So the Metalenz is located at 0 value here. And we can see that for different angle of incidence, the focal point is remaining at 10 micrometers in that case. And we can also have a visualization of the field over the focal plane. And it has been done a validation using FDTD because it was really important, really, mandatory on our side to validate the accuracy of the MetaOptics designer engine for the propagation aspect. Then we can also talk about large field of view and achromatic Metalenz. It was already mentioned earlier by some other speaker how challenging it was in terms of efficiency, and indeed it is a really challenging design. And so on our side, we were using this type of of Meta-Atoms library or rectangular shape. So it's coming from an idea from the University of Paris. And now having this so Meta-Atoms library, we generated the Metalenz surface in order to have, so for 1.3 micrometers and 1550 nanometers, an equivalent focal distance for different angle of incidence. Here it's at 0 degrees and at 40 degrees. And again, it's by adding some optimization target inside the design case. We can also combine refractive lenses and Metalenz. So from using Code 5, it's our ray tracing software, we are able to simulate, optimize a curved lens, let's say a classic lens, and having the definition, so we can generate the definition of this lens inside Code 5 and bring the information into a MetaOptics designer. So in that case, we are loading a sec file, sorry for the details. And then having this definition of the classic lens, we can add another surface, a Metalenz surface, after this initial lens. And the idea of this meta surface is to correct even further the aberration, the achromatic aberration. And what we can analyze from here, so we had in blue and green the focus shift after the refractive lens, and now we can also have a view of what would be the focus shift by after optimization of the Metalenz, and it's getting much better. So it's a kind of meta corrector after a classic lens. And just to conclude this presentation, Rob was mentioning with the Gemini project the capabilities or maybe new perspective for a designer using the polarization effect of the Metalenz. So here it's an example of polarization selective hologram. So I was using two images, so one unique meta surface, and I launched the optimization to get the first image for the circular left polarization and the Happy New Year logo for the circular right polarization. And at the end, so the speed of the optimization is by a factor 20. So we are talking about few minutes. At the end, I had this type of image at the focal plane for this meta surface. And I was using a library based on a rectangular shape, and the parametric factor to change the phase delay of the meta atoms was the orientation of this rectangular shape. So to summarize my presentation, MetaOptics Designer, it's a unique, fully automatic tools to design Metalenz and meta surface using inverse design algorithm. So our target is really to simplify and speed up the workflow, the design flow for the designer with a minimum input requirements. Designer at a different level of expertise can create novel Metalenz design quickly and easily, and it has been validated by our FDTD engine to make sure that the accuracy of the optimization of our new modules MetaOptics Designer. Thank you.
Thank you, Maryvonne. This does look like a very useful tool for many people in the audience. So the session is now open for questions. Please raise your hands if you have a question for Marianne. Olof from Eclipse Optics.
Yes, hello, thanks for the nice presentation. Can you comment on how the design would look if you need a hybrid solution with a refractive element? Would that be the same?
Could you comment if you need a high resolution?
A hybrid, like a refractive element combined with a meta optic.
So, so you are talking about referring to this design case. So, by it's really depending the projects that you will have and the type of targets for the meta-optics layer that you will have after the refractive lens. So what you will so here it was for the achromatic correction in this specific case. And so we were using a refractive lens having already a certain compensation down inside code 5, but then we went further due to the Metalenz surface, but it will really depends of what is already down. So what is the overall target of the optical combination and what is already down on the refractive part of your design.
Okay. Yep.
Do you have something in mind?
Maybe, yeah.
Well, if you have something in mind, Olaf, don't hesitate to come to Maryvonne or
yes,
or come to me, and I put you together in contact.
Sure.
All right. Is there any other question? Well, if not, it has been a long session, so I suggest that we start wrapping up. Thanks again, Maryvonne. It was an excellent presentation, and let me just share a few closing remarks with you. So this was the EPIC Online Technology Meeting on Metamaterials and Metalenses, presented to you by EPIC, the European Photonic Industry Consortium. We have heard 7 beautiful presentations today from Samsung Advanced Institute of Technology, from Applied Materials, from Nil Technology, as well as Metalenz, EVGroup, PlanOpSim, and Synopsys. I would like to take this opportunity to thank my team. This is the EPIC team, 10 people that support you with on all kinds of aspects related to photonics. We provide technology consulting, networking opportunities. We provide the mentorship in photonics, as well as market reports and access to the new markets for your company, and as well as HR support and investment opportunities. This is the first event of the year, and there are already several events announced. So among the online meetings, just like the one you're watching right now, there is one upcoming seminar on the January 16th devoted to marketing and the CEO training. And after this, we continue with technology meetings on several topics such as laser-based manufacturing for implants, bioimaging. We talk about quantum metrology and quantum sensors, as well as micro LED for automotive applications, and about photonics for climate change monitoring. So please save the dates that are on your screen right now. And the next opportunity to see us offline in person, this would be on Photonics West in San Francisco in the end of January. And with this, I'd like to thank you all for your attention, and also to thank the sponsors of this event once again, the Nil Technology, Corning Lasers Technology, and axetris. Thank you very much, and see you next time.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.
Thank you.
Thank you, everyone. We will keep the room open for a while. So if you have an opportunity to discuss